So, in classical mechanics, well, non-relativistic mechanics, I guess, our energy is equal to the momentum squared plus over 2m, which is our kinetic energy, plus our potential energy. In relativity, however, our energy is equal to momentum squared times c squared plus the rest energy squared, which, for those who don't know, is mc squared. When you get rid of the momentum, it stops moving. It just equals rest mass times speed of light squared. So that's the energy due to motion, assuming it has no potential energy. You subtract off to get the kinetic energy the rest energy. That's the energy due to motion. And then you'd add on, of course, the potential energy to get the true total energy. I said that kind of weird, but those who know what I'm talking about know what I'm talking about. Well, okay, we're going to pull out a factor of E sub 0 out of the square root. This is our kinetic energy. As the function 1 plus x, the square root of 1 plus x, as x goes to 0, you can show this with the Taylor series expansion, it equals approximately 1 plus 1/2 x plus more corrections. So ordinarily, p squared over c squared, EO squared, 2 plus 1, EO, EIO. Yes, I just said that. Those will cancel out, and our kinetic energy, p squared over c squared over 2EO equals mc squared, so the c squareds cancel out, and p squared over 2m. So our kinetic energy approximately is p squared over 2m. But what if we want to consider when it's moving at pretty quick speeds, not like close to the speed of light, but way closer than normal? That p squared over c squared over E sub 0 squared is not going to be quite as small, and we have to include more corrections than just the 1/2 x and give us a relativistic correction. Well, let's compute. You can do this with the Taylor series, but it's kind of time consuming, so I'll just say 1 plus 1/2 x plus ax squared. That'll be and we're going to neglect terms that are higher than x order x squared. 1 plus 1/2 x plus ax squared equals 1 plus 2 1/2 x plus ax squared plus 1/4 x squared plus ax cubed. Okay, so those are all going to be higher order. E equals 1 plus x plus a, 2a plus 1/4 x squared, which must equal to first order 1 plus x, which means that a equals -1/8. So our series will approximately be, as x goes to 0, kind of rushing this, 1/8 x squared. Alright. So that'll just give us our p squared over 2m like we did for the 1/2 x part, plus 1/8 e sub 0 p to the 4th, c to the 4th, EO to the 4th, because that all squares out, and e sub 0 to the third because that factor cancels out. And we're going to replace that. MC squared, M cubed, C6, that'll cancel out, C squared. So kinetic energy is equal to P squared over 2M, P to the fourth, 8 M cubed, C squared. So that's like when you get, that's a correction to the kinetic energy. Well, usually in quantum mechanics, the usual procedure is to convert these all to operators. So that will become our derivative with respect to x times negative I h bar. You'll just plug that in, and you'll have a correction to it. So really, our Schrodinger equation with a first order correction would go like that. Be another operator. And we'll go off the rest after our break.